Now in the first question we have an aircraft flying from Aberdeen to Glasgow. The route that it takes, it travels 140 kilometres due south, then 130 kilometres due west, and we're asked to find the magnitude of its displacement. So we're not interested in the directional nature of displacement. Recall, displacement is a vector. So we're invited to draw a scale diagram or otherwise. In questions like this that have got more than one part to them, I always suggest a scale diagram right away so you can use that for other parts of the problem. First of all, we need to have a good scale. Well, in this particular case, our diagram has to fit into the space provided. Now that's 9.5 centimetres deep because I measured it. So our diagram has to fit into that space. Now when you're drawing scale diagrams, always try to use as much of the space as possible without overcomplicating the scale. In this particular case, what I can do is I can use a scale of 1 centimetre to represent 20 kilometres. Therefore, a 140 kilometre line will be 7 centimetres and a 130 kilometre line will be 6.5 centimetres. Always go in with a 6-inch ruler, they're easier to manage. Now it's easy to draw a straight line with a ruler, but it's not quite as easy to draw a perfectly straight horizontal line or a perfectly straight vertical line. You have to align your ruler with what's on the page. In this particular case, to draw this triangle, what I'm going to do is I'm going to align my ruler with the margin on the side and the barcode in the middle. Then I draw my hypotenuse. When I've done that, I then take my measurements. And as we can see, I get a 9.5 centimetre hypotenuse. That corresponds to 190 kilometres, and that is the magnitude of my displacement. Now in the next question, I'm asked to find the direction of the displacement. Now, then you bring up a protractor. You measure the angle, and that's 43 degrees measured from south. But remember, all these bearings are referring to north. So what we do is we start at 0, 0, 0 north, and we go round clockwise until we get to our vector. So that's 180 degrees plus 43, meaning your bearing here, or the direction of your displacement vector, is 223 degrees. So now we're asked to work out the average speed of the aircraft as it goes from Glasgow directly to Aberdeen. So the formula that we're going to use is D is equal to V bar times T. Since you've got d on the left, the v bar has to be average speed. Put your values in, and you get your average speed to be 110 meters per second or 380 kilometers per hour. Either will do. So in this particular case, we're using displacement S is equal to v bar times t, where v bar is the average velocity. Now it so happens in our particular problem, the distance travelled was the exact same as the magnitude of the displacement, which means the magnitude of the velocity is the same as the average speed. So the magnitude of our velocity is simply 380 kilometers per hour. Now its direction, well, remember we're making a complete U-turn from our first vector, so we have to subtract 180 degrees from it. We're not going southwest anymore, we're going northeast. So we need to take 180 degrees off it. So our final answer is average velocity is equal to 380 kilometers per hour, 043, and that's the answer. Now the second question, we're asked to draw a graph. Now the first thing we do with graphs is we identify the independent variable and the dependent variable. Now the independent variable is normally drawn on the left of the table. In this case we see its release height. The dependent variable depends on the release height, and we'll normally plot that on the y-axis, the vertical axis. Now when we've done that, we decide what our scale should be. Now with this graph paper here, I've decided the best graph, the graph that takes up most of the paper and is easiest to draw, will occupy 20 boxes for 1/10 of a meter on the horizontal axis and 10 boxes for 1/10 of a meter on the vertical axis. We then plot our points as carefully as possible, taking our time. Then when we've done that, we find out what the horizontal range would be for a release height of 22 centimeters or 0.22. Now we're asked to present an improvement to the investigation. Well, previously the boy or the girl who did the investigation simply watched where the marble fell, kept that in their mind and went and measured it, perhaps without even taking their eye off the spot. Now there's a better way than that. We can put a grid there and we can film the experiment, so we can film where the marble strikes the grid, and after that we can analyse it. That would represent an improvement. The next question asks us to suggest another variable we could investigate. Well, one could be simply the mass of the marble. Then we're asked to suggest how we would carry out the experiment. Well, for changing the mass of the marble, we have to remember we have to keep certain variables the same. So we'll need to keep the size of the marble the same. Now, to keep the size of the marble the same and change the mass, we would need to use glass of different densities. That would do it. And we need to find a suitable range, maybe between 1 and 3 grams or whatever. Maybe 1 and 5 grams if that's possible. Then the other variable we need to keep the same is the release height. We need to keep that the same. Then we would carry out the experiment with 4 or 5 different marbles with different densities, therefore different masses, the same size, and see if we got a different result. So we're on Mars and we've got a question now on forces, and the question is this. Given the mass of the space rocket is 1.6 times 10 to the 6 kilograms, calculate its weight. So what's the difference between mass and weight in terms of forces? Well, the best example is the supermarket trolley example. Suppose you've got 2 trolleys, one's got 25 kilograms and one's got 50 kilograms. The one with 50 kilograms will be harder to push to the left and right than the one with 25 kilograms. And that's pretty obvious. And it doesn't matter what planet you're on, it's always the same effort to push these things backwards and forwards. Always a greater effort for the one with a larger mass. But weight, on the other hand, is more to do with vertical motion. So if I wish to find the weight of something, I'm holding it in my hands and I'm judging its weight. But I will get a different answer if I'm on Mars or any other planets. It's a lot harder to pick up something on Earth than it is to pick up something on Mars, because the gravitational force acting on a kilogram or any mass at all on Earth is always greater than that on Mars, and that's what's known by the weight. It's the force a planet exerts on a body of mass m. So on Earth, for example, you wish to find out the weight of a 1 kilogram body, that will weigh 9.8 newtons. If you wish to find the weight of a kilogram body on Mars, that will be 3.7 newtons according to this table. So weight is a force acting upwards, acting downwards I should say, and mass is a measure of how hard it is to push something to the left or to the right, and it's the same on all planets. 4.8 times 10 to the 6 newtons on our space rocket, and that is the force our space rocket has to overcome in order to simply rise off the planet. In other words, planet Mars is exerting a force of 4.8 times 10 to the 6 newtons on our space rocket, and that is the force our space rocket has to overcome in order to simply rise off the planet. So now we're asked to draw our two forces acting on the rocket as it rises from Mars. Now one force down the way is its weight, as we've already discussed, and the force up the way is the rocket upthrust, and those are the two forces there. Always draw them with a ruler and always put your arrowheads on them as well. Now we're asked to find the acceleration of the rocket as it rises from the surface of Mars. Well, the formula used here is F is equal to m times a, but we have to remember F is always an unbalanced force. So I put in the wee subscript U to indicate that. So the unbalanced force here is the rocket upthrust, take away the rocket's weight, and that's equal to the mass of the rocket times the acceleration. Put them all in the formula. Upthrust, take away weight, is equal to m times a, and you get an answer of 5.5 meters per second, and that's the acceleration of the rocket as it rises from the surface of Mars. So what happens to the rocket's acceleration as it rises? Well, the rocket rises, it's burning up more fuel, therefore it's getting lighter, and we're told the upthrust is the same. So if you use F equals ma, the mass is getting less and upthrust stays the same, then its acceleration has to be increasing. So we read the passage and we're told that Rigel is 860 light years from Earth. That means it takes 860 years for light to leave Rigel and get to us. This means if light left Rigel in this instant, it'll take 860 years before it gets to Earth. How many meters is that? Well, we'll have to use distance is equal to velocity times time. Now the distance is what we're looking for. The velocity, this is the speed of light, and the speed of light is 300 million meters per second, or 3 times 10 to the 8 meters per second. And what we have to do then is multiply that by time, and it's a number of seconds in a year. So that is, how many seconds are in a year? Well, there are 365 and a quarter days in a year. There are 24 hours in a day. There are 60 minutes in an hour, and there are 60 seconds in a minute. Multiply all these numbers together, then multiply it by 860, and you've got the number of meters from Earth to Rigel, and it's actually a colossal distance, one that we can't imagine really. Next question, easy wee question for 1 mark. What's the speed of the debris after a supernova explosion? Well, we're told the debris is going at a speed of 5% the speed of light. So it's just 5% the speed of light, and that's our answer. 0.15 times 10 to the 8 metres per second is the speed of the debris. Next question is this. Well, suppose there's a supernova in the Beagle and that happens today. Why wouldn't we know about it? Well, that's because it takes light 860 years to get to Earth. So any light produced on Beagle today will take 860 years to get here. So if the supernova was today, we won't know about that until 860 years. So the inhabitants of Earth, 860 years into the future, they will observe it, but no inhabitant of Earth will observe it before then. Now the last question it asks us, how does this absorption spectra enable us to identify the elements present in stars? Well, let me explain to you how an absorption spectra is produced first of all. Suppose we've got starlight. Suppose we've got a beam of pure white light striking a prism. The light will refract through the prism and you will see a spectrum of colours. Now if we let a gaseous element creep into the path of the light, that gaseous element will absorb certain colours and you won't see them in your final spectrum. They will appear as blank or black lines. Now we know what colours are absorbed by each gas. So by comparing our starlight spectrum with what we know about absorbed colours from the gaseous element, and if it matches, we know the element present in the atmosphere of our star. And that's how we use absorption spectra to identify the elements in stars.